Okay, so hi guys. As you just said, I'm Pietro, and I'm from the WUSEC group in Amsterdam. And this talk today is going to be about glitch. And the title is Glitch Chronicles because it's not just about glitch, which is a browser exploit, but it's also how the whole story evolved while working on this. And I work on this project with Cristiano, Herbert, and Kave, which are the three main professors at the WUSEC group in Amsterdam. So let's start with what glitch is in a couple of sentences. So glitch is the first rammer exploit from JavaScript on mobile. So before this research, there was no proof of rammer bit flips from the browser on ARM platform. Not only is the first one, but it's also the fastest JavaScript-based rammer exploit. So previous research on this kind of attacks was taking at least 45 minutes to get a bit flip on mobile on the browser, whereas this one takes less than 2 minutes to exploit the browser. And finally, which is probably the main contribution of this work, is that glitch is the first GPU-accelerated rammer bit flips. So we actually show that it's possible to trigger these bit flips not only using the CPU, but also using other means such as the GPU. So now let's start a bit with the history of this work. So let me introduce you to the Chronicles of glitch. So here is a bit of a timeline, and that little guy over there is me. And it was mid-2016, I was looking for a thesis for my master. At the time I was studying TU Delft, always in the Netherlands, but a different university. And I went to a conference, and there was Cristiano, one of the professors that eventually became my supervisor, that was talking about DRAM, ROM, and bit flips, and I was not quite aware of any of that. I was really confused about everything he was talking about. So I started studying a bit because I want to ask him to be my advisor to start a thesis with them. So I started studying DRAM, and when you think about DRAM, this is what you think about, right? So you have these DIMM modules that you put in your system, and just stuff them there, and they have memory enough for you to work on. But where the magic happens is actually inside these ones, which are the chips. And these chips actually contain a memory array, actually multiple of these memory arrays. And in these memory arrays, you actually have cells. So every single one of these, it's a cell. And these cells contains capacitors. And the capacitors leak charges over time. So that's how the capacitor works. They don't retain charges forever. And as a consequence, you actually need to refresh them every now and then. Otherwise, you will lose your data, and that's not what you want to get out of DRAM. And the way DRAM read works is basically you would have data in memory. So let's say you want to read something from row 2. Let's say you want to read a byte from there. What you need to do is you activate the row. And activation is the process of bringing that row to the row buffer, which is the last row down here, which serves as a cache basically for DRAM. So once you get the data there, you can read it out from there and bring it to the CPU. Now, reading from a capacitor means discharging the capacitor. So the data that's in the capacitor is lost for now, which means that if you want to save this data and not lose it for the next usage, you need to actually restore it back to the row where it was. And this action is called pre-charge. So every time you read something from there, you need to, at the end, close the row and pre-charge it. Now, what the researchers have discovered is that if you actually perform specific access pattern in DRAM, you can actually cause some disturbance errors inside the DRAM itself. So what they discovered is that if you choose two aggressor rows with a victim row in the middle, and you access the aggressor rows fast enough, which means you activate them fast enough, some charges in the victim row, some of the cells may start leaking charges over time. And soon enough, you may get a corruption in this data. So you can trigger a bit flip without actually accessing the data. And this is quite important for two reasons. First of all, you break the property of integrity of this data. And as a consequence, you don't get any more data you expect from DRAM. So you wouldn't expect that data that's in DRAM gets compromised without really being accessed. And second of all, which is the most important thing of this phenomenon, is that it's reproducible. So once you find a bit flip, you can reuse it later on, which means that usually the way this attack works is that you just allocate a lot of memory, you look for bit flips in these DRAM chunks that you have. Once you find a bit flip that you can reuse later on for an exploit, you release that part of memory so that you can reuse it for the exploit itself. So back to the timeline, then I was studying a bit about this rammer phenomenon and how it was exploited, and it turns out it was actually pretty recent as a research topic. So the first paper on this topic was in 2014, where they were showing it was possible to actually induce these faults. And then in 2015, Seaborn from Google Project Zero and Dulian, I hope I'm saying the name correctly, they showed the first root exploit on using Rammer. So what they were doing were flipping bits in the page table entries. So by flipping these bits, they could basically access any memory they wanted in the system, then having root privileges. Afterwards, some people brought it to the next level, showing it was possible to do it also from JavaScript. So they were showing that it was possible to trigger bit flips from the browser. At the same time, also, Eric Bosman from our group was working on this project called Didupas Machina, which was using, again, these bit flips to break out of the Microsoft Edge sandbox. And also, Kave, one of the authors of also this work, was working at the same time on breaking the cloud, using also these bit flips. So it was just compromising some RSA keys in virtual machines to get control over a different machine just by triggering a bit flip. So I was just making a recap, and I thought, okay, so you have a root exploit, 2 JavaScript exploit, 1 on the cloud. And I thought, well, the next step, of course, is just looking at the phones. So can you actually do it on the phone? So I pitched the idea to Cristiano, and Cristiano was like, well, you came a bit too late. Actually, there is Victor, another guy from the group that just did this, and we're publishing now a paper about it, which shows that you can actually root deterministically Android phones using Rammer. And so I thought, okay, cool. I still don't have anything to work on. But then, when the paper came out, Victor was bragging on Twitter about his super awesome research, and rightly so, because it was a really cool project. And then he was saying, well, I wouldn't be surprised if we could pull this one also from the browser. And this was a bold statement, because it's actually not that easy, and people that done it on x86 already knew it was not that easy. So the garage called him out on his bluff, basically, and he said, well, I would love to see it happen. So challenge accepted. I had something to work on, and it was actually a really challenging task. So I started looking in how you actually develop this kind of attacks. And when you think about any kind of attacks, usually you start by some attacker primitives. And in the case of Rammer, the primitives that you need are, first of all, you need to have fast memory access. So the problem here is that when you actually access data from DRAM, you don't always want to go to DRAM because it's very slow. So what CPU vendors have done since forever, actually, it's not something new. They put CPU caches in the middle. And memory access coming from DRAM usually takes around 100 nanoseconds or even more. Whereas a memory access coming from the L1 cache, it takes around 6 cycles, if I'm not mistaken. So it's quite different, the latency that you get between the 2 different memory accesses. The problem here is that if you want to hammer, you will go to DRAM the first time, so it checks the caches, then it will go to DRAM, and then it will bring the data to the cache before giving it to you, to the CPU. And this doesn't help because you want to access data from DRAM, not from the cache, so you need to have some tools to remove it from there. And so what they usually do is to use the CLFlash instruction in native programs. And this is an instruction that allows you to basically remove the data from the cache. So you just provide an address, and the CLFlash instruction will just remove the cache line from the cache, so you can access it again from DRAM the next time. Now, clearly, this is not available on the browser. So what they invented for browser was to use eviction sets. This is a technique that is already known for cache attacks. So they implemented the same thing now for Rammer attacks. And the way this works is basically you start accessing a bunch of random addresses from memory, which are, I mean, they're not quite random, but some addresses that you can use to remove data from the cache. And you fill up the cache until at one point this data gets removed and you can access it again. Now, clearly you need to do this quite fast, because otherwise you won't be able to get your bit flips. The second primitive instead is you need to have a contiguous memory to trigger these bit flips, because as we mentioned, you want to have 3 contiguous rows in memory, so this needs to be adjacent. And this is not a hard requirement. You could also do it with a single-sided hammer, where you actually just hammer one row and then you get bit flips in the two neighboring ones. But this is much more powerful, so usually people opt for this version of row hammer because you get more bit flips and more control over them. The problem here is that when you allocate memory, it's more complicated than what you expect. It's not just you get the contiguous rows after you allocate some kilobytes of memory. So what happens, for instance, when you do a malloc of 20 kilobytes is that you allocate a bunch of pages in your virtual memory. And then these pages then gets translated into some physical pages in physical memory. And while the one in virtual memory may look contiguous, actually in the physical address space, these are scattered around. They're not exactly contiguous. And this depends on the allocator. So the allocator will try to give you the first available page. So it will try to avoid fragmentation and just provide you with the smallest chunk available at that time. And then after this, there is also another step. So you have the memory controller that decides where to map it to DRAM for you. So you'll have quite a few steps of indirection that provides you with these contiguous rows. And earlier we were mentioning that DRAM is like this, but actually DRAM is much more complicated than this. But so you have actually the CPU, which is connected to multiple channels, and in the channels you have multiple DIMMs, and then every DIMM has multiple ranks. So the front and the back of DRAM will have both sides chips containing data, and then all the chips will have multiple banks, which are the one that we showed earlier, made this way. So the memory array is actually inside the banks. And the banks span over all the chips, so you will have like an array buffer on all the chips, row buffer in all the chips that will provide you with the data. So how do you get contiguous memory? Well, the solution usually was to use transparent huge pages. And this is a way to optimize the address translations. So what the operating system will do if you allocate a 3 megabyte page, for instance, it will try to provide you with a big chunk so it doesn't have to have page tables for all the 4 kilobyte pages. So in the physical address space, what you will see is, again, you will have some scatter pages of 4 kilobytes, but then since you have 3 megabytes, you can also provide a huge page, which is the big one. And this one is of 2 megabytes of size. Now, when you control 2 megabytes of the physical address space, you'll have more fine-grained control over multiple rows on DRAM. So you basically can get addresses that will map to the same channel, same DIMM, same rank, same bank. And then with this, you can actually perform more accesses that will trigger the bit flips. Now, this is all cool, but this is the way they were doing it on x86. How does this work on ARM? Well, CLFlash, it's a privileged instruction, so we cannot use it. And we couldn't use it anyway because we want to do it from the browser, so this is not really of any help. And eviction sets also were not usable from JavaScript, from ARM. And Victor, that did the drummer project, tried at the beginning to get bit flips using eviction sets. And what he discovered is that the caches on ARM platforms are too large and they implement a random replacement policy. And what does this mean? Well, for our attack, it means that if you want to access the two aggressor rows, so row n-1, you will bring it to the cache. Then you will do the same for n+1 and bring it to the cache. And we'll just place like in random places within the cache set. And then you will start evicting. So you access a lot of memory. And sometimes some data that you just use for eviction will evict data that you just evicted yourself. So this is actually not very convenient. And at one point, you will get a memory access that will remove the data you want to evict from the cache. And then you can read it again. Now, as you can understand, here you have quite some problems because by having a large cache, it means that you will require a lot of memory accesses to remove them, to remove the data you want to remove from the cache. And the second problem is the random replacement policy, which doesn't allow you to use the same access pattern over and over and again, because by having a random replacement policy, maybe once it works, and the second time maybe it doesn't. And this is quite problematic in this kind of attacks, because you want to have reliability, clearly. And contiguous memory, well, you may guess also that on the transparent huge pages are not available on ARM. And as a consequence, we cannot use also these, so the browser doesn't rely on any of these. And I mean, actually, they cannot be allocated on ARM platforms because they're not supported in most of the platforms. So then I went to Victor and asked him, so how do you do it on ARM? And he answered Ion. And Ion, basically, it's an API provided by the Android kernel that provides you with the DMA memory. And DMA stands for direct memory access. And this memory that's usually used by peripherals, such as the GPU, for instance. And as a consequence, it's uncached and contiguous, or it can be uncached and contiguous, which means that you might want to have uncached memory to avoid coherency problems between the different peripherals, the CPU and the digital signal processor or whatever else. And contiguous because you might not have an MMU, which is the one that takes care of the translation between virtual and physical memory. So you want to have already the contiguous chunks. Now, again, this is a low-level Android kernel API, so it's not available from the web. So I thought, okay, we're doomed. We cannot do anything here. And then I started thinking again about this problem. And I thought, well, they used Ion because it's used for peripherals. So what if we change the attack vector and we look at different peripherals that might have contiguous memory? And what's the attack vector here? Well, you have your JavaScript code running in the browser that would run again on the CPU. So the browser runs on the CPU. And eventually will perform your memory accesses on DRAM. The thing is, on a modern system, you don't have a CPU, but you have a system on chip. And the system on chip contains a lot of stuff nowadays. So you have a CPU, you have a GPU, the 4G modem, digital signal processor. Then you have even in the fancier one, now they have some neural network chips because machine learning is the future. And the JavaScript code we run on the CPU, but you can also access the GPU from the browser through the WebGL API. So the whole hope was that maybe the GPU would provide you with some uncached and contiguous memory, such as the Ion memory. Now, the primitives that we need now are fast memory access and contiguous memory again, but we need to study how to get them. And first of all, we actually need to understand how to get DRAM access in the first place, because we have no clue on how to do this from the GPU. So we're going to go over every single one of them to understand how we got them from the GPU. And to understand how we got access to DRAM in the first place, we need to understand how the GPU works. The GPU serves the purpose of helping the rendering pipeline. So it aids the rendering of some graphics. And it runs on 4 stages mostly. The first stage is to get the input provided by the CPU. And this input comes in the form of vertices. And this vertices gets passed to the GPU, which runs these programs which are called shaders. So the shaders are actually the programs that the GPU runs. And the vertex shader performs computation on these vertices, geometrical computations, so translation or rotations. And once it performs these operations, at the output, it will provide a polygon. And the polygon basically is the connection of these vertices. So you will have the edges of this polygon and all the fragments within this. So all the pixels are within this triangle are the fragments that eventually will run through the fragment shader. The fragment shader instead has the purpose of coloring the pixels, the fragments. And so it will perform some computation again to decide the color of these fragments. Now, if you don't want to play just Minecraft, where the graphics are pretty horrible, you want to use some textures for this. So the GPU provides some ways to also get some external inputs from DRAM again. And these are in form of textures. So you just store your data, for instance, in this case, a wooden texture in DRAM, and then you can color your triangle using the texture that you have in memory and have a wooden triangle. And eventually you get the output to the frame buffer, which is basically the screen of your system. And you will see it again on the screen. Now, the way this works on the architecture, so this is an example of how the architecture may look like. And these are the main, the ESP are the main cores of the GPU, which are the stream processors. And you have multiple of these because you try to parallelize as much as possible the operations on the CPU, on the GPU. And these are the ones running the shaders. So they will start by fetching the vertices from memory. and then running the vertex shader on these vertices. So the output is going to be the polygon that I just mentioned, and after that, the fragment shader will start running on every single fragment within the polygons. During the fragment shader, you will call these TP, which are the texture processors. And the texture processors are the one in charge of getting the data from the textures. So they will call the textures and fill in the fragments with the texture data. At the end, you will just output everything to the frame buffer and be done with the whole process. Now, we look at what DRAM access points you have, and as you can see, you have these three. You can read the vertices, read in the textures, or write to the frame buffer. So we had to pick one, and we decided to go with the textures because it was the most predictable. So the problem with the vertices was that they run in parallel, so the stream processor just run in parallel the vertex shader, so you don't know exactly how to coordinate the memory accesses if you allocate enough vertices to cover multiple rows. With the frame buffer, instead, the problem is this thing called OCMM, which is the on-chip memory. At least on the mobile system, they usually have a bigger cache that stands between the shader, the stream processors, and DRAM. And this stops again our access to DRAM. While with reading the texture, it's actually a bit simpler. I wouldn't say trivial, but still a bit simpler. And the way it works is basically you would have, this is an example of a shader. And what you do is basically you call this texture2d function with the texture as a parameter, as an input, and some coordinates as an input. And once you know the mapping between coordinates and offsets in a buffer, it's basically as just referencing a pointer or just accessing an index inside an array, basically. So you just need to know where you need to touch, and then you can just use this within the GPU, and you can program the GPU to run specific operations. So we do have our first primitive, which is DRAM access. Now, is this access fast enough? So going back to the architecture of the GPU, as you can see here, we have two levels of caches, which we didn't pay attention to earlier. And these, again, don't help, because as we said, the cache are the one they're stopping you from accessing DRAM. So here, when you run a shader that accesses the same offset twice, what would happen again is you just get the data the first time. So the texture processor will go to DRAM to get the data. Then we bring it to the L1 cache. And the next time you will get it directly from the L1 cache. So we'll stop your memory access. Now, these caches were completely unknown, so we didn't know how they were working, so we had to reverse engineer them. And this is actually quite interesting, but unfortunately, I don't think I have time to cover this part. But the interesting bit of this is that the nature of these caches is completely different from the one of the CPU. So these caches are actually small compared to the CPU one. So we can compare from megabytes to basically kilobytes of textures. So the CPU cache are usually in the order of 6 megabytes, for instance, on modern systems, and these are in the order of 32 kilobytes. And they implemented deterministic replacement policy. And this means that in our case it was a FIFO replacement policy. So what we'll do in this case is you would read the row n-1, you place it in the cache, then n+1, and you place also that one in the cache, and then you can start evicting. And the eviction here is going to go sequentially, so you can always perform the same access pattern, and you will be sure that at one point, after n accesses that you know the amount, you will remove the data from the cache, and then you can access it again to start hammering again. Now, this is cool, but is this fast enough? So this plot comes from Drummer, actually. So this is a plot that Victor made, and he was studying how much latency how much you can wait between two memory accesses to get bit flips. So the number of NOP instructions on the x-axis are the one that basically are put between the two memory accesses, and on the y you have the number of observed bit flips and the time. So as you can see that the time increases by increasing the number of NOP instructions, and at the same time the number of bit flips decreases. We studied how much it was taking for us to perform a memory access with our access pattern that we developed for evicting and hammering at the same time. And it turns out we run in around 180 nanoseconds. So every 180 nanoseconds, we perform an access that we can use for hammering, and which means that we can actually get B-flips based on this plot. This plot was made on a Nexus 5, and we ran all our research on this Nexus 5, basically, so it was meaningful, the comparison between the two studies. So yay, we're fast enough. So we celebrated after that. And we have fast memory access. Now the next step is how we get contiguous memory. Now for the contiguous memory, as we said, usually the operating system tries to avoid this fragmentation. So in this case, this is again the way we represent DRAM. It's a simplified diagram, but it's quite representative. And every single one of these, it's one page. So these are going to be 4 kilobyte, or at least part of a page maps to that row. And when you want to allocate memory, in our case textures, what you will do is basically allocate texture with this function create texture, and then you will fill it. And you need to fill it because they're lazily allocated, so otherwise you won't allocate actually any memory. And afterwards, what will happen is that the operating system will start providing you with the smallest possible chunk, which is 4 kilobyte. So we'll provide you with these single pages available. At one point, you will get some contiguous chunks. So these two, for instance, are already contiguous, but they're just 2 contiguous pages, so that's not enough for you. And eventually, you will start getting a big chunk that is big enough for you to perform your rammer attack. So this chunk is clearly hammerable, while the other one is not hammerable because you cannot have enough memory that you control. Now, this is cool, but how do you distinguish the two of them? And the answer here, it can be the simple answer is basically you can just allocate a lot of memory. And at one point, you will get chunks that are contiguous by default, because again, as we said, we try to avoid fragmentation. So at one point, you will provide you with a big chunk because they're the one that gets allocated as last ones. But the answer that we decided to go for, it was a different one. So we decided to implement side channels. And the idea was that I want to show that the GPU is not only good for triggering B-flips, but it was more of a widespread issue that basically we're introducing a new attack vector. So not only for rammer attacks, but also for timing side channel attacks. And the side channel attack here, it's on the way DRAM reads work. So as we mentioned, a DRAM read, let's say we want to read this specific page or one address from that page in DRAM. What you need to do is you activate that row, you bring it to the row buffer, and then you read from there. And eventually you need to send it back. So the side channel here that we can use is simply touching addresses from different textures in memory sequentially. So you just touch these three textures, for instance. And what the GPU will need to do is to access the first one, bring it to the row buffer, and read it from there, then send it back, then bring the second page, which is on a different row. So we generate a conflict, and then you can read it from the row buffer. And eventually also a third one, which comes from the previous row, but of course the CPU doesn't, the memory controller doesn't changes the access here. So we provide you with this one eventually. And this clearly is low. On average, at least, like it's much slower than a different access pattern. But the point is that it's very noisy. So you will get this very noisy signal by shifting the access pattern. So you will start like accessing all these pages by shifting by one every time. And you will see a big standard deviation and slow memory accesses. What happens instead when the memory is contiguous, if you want to access 3 consecutive pages, is simply you get this row, bring it to the row buffer, and then touch them all, and then send it back. And this provides you with a very fast and clear signal. So you can clearly distinguish between the two different access patterns. Now, to detect this side channel, clearly we need timers. And timers are a big thing in browsers because of side channels such as Spectre now. So right now, all the browser vendors are trying to disable all the timers that are available to the attackers. Because if you don't have the timers, you don't have the side channel, right? So that's the mentality on this mitigation. So what we did, it was we tried to find some timers that we could use to detect accesses made by the GPU. And we found two different families of timers. The first one is based on the disjoint timer query extension. And this is pretty nice because it provides you with an interface such as clock get time. So basically you can just query it and it will provide you with a timestamp. And the resolution of this timer depends on the driver implementation. So by specification, it can be up to nanoseconds. Then it depends on the system, how it implements the API. And also on the browser itself, so the browser may cap it. So for instance, that was what was happening in Chrome, but that was not what was happening in Firefox. And it provides you with a high resolution, clearly. And also it's nice because you could also use an asynchronous callback. So you could just say, please time for me this memory access. You tell the GPU, okay, run this operation and tell me what's the time. And at one point you will get a callback telling you, okay, this was the result. So no noise, nothing. So that was pretty nice as a timer. However, this is an extension-based timer. So to prove our point that the mitigation of breaking all the timers was not a solution, we actually went a bit further. And we found another timer based on the WebGL sync objects that are fence objects that are used in the WebGL2 specification. And these fences basically are used to synchronize the CPU and the GPU operations. Now, clearly, since it's a synchronization point, these are more coarse-grained and they're quite noisy compared to the other ones. But still, they serve the purpose of what we need to do. And actually, for our attack, they don't really matter because even if you have a low resolution for these timers, you can actually just increase the number of accesses that you perform over the same access pattern, and we'll get the result no matter what. And the cool thing of all this is that actually you can revive all the attacks such as Spectre in the browser by using this timer instead of the one that they just disabled. So you get all the primitives now. The question is, what do we do with these primitives now? And the answer is we build an exploit, because otherwise it's pointless. So we need a proof of concept to show that it's actually a threat, otherwise there was nothing to show this. And our target was Firefox on Android. And the reason why we chose Firefox was simply because it was easier to exploit than Chrome. Actually, all the previous research, so everything explained so far, all the primitives, we first found them in Chrome. So the whole study was done in Chrome. But then when it was time to build the exploit itself, we moved to Firefox because there was more documentation online. So for instance, there was a really nice FRAC article by RP, and then some nice blog post by Saelo, which he might be actually playing now for the CTF. So I'm not sure if he's here. Anyway, what is glitch? How does it work? Glitch is flip feng shui in JavaScript. And flip feng shui is a term that we coined in our group. And it runs in 3 stages, basically. It's memory templating at first. So what you need to do at the beginning is basically allocate a lot of memory and look for bit flips there. So you just allocate all this big chunk of memory, scan for bit flip to find bit flips that you can use later on for your own attack. Then you have memory massaging, which is the moment when you actually found the bit flip and you want to release this memory to trigger some allocation of a victim data structure. And eventually the exploitation, which is the interesting bit here and which is the one we're gonna analyze. And the exploitation is actually how you compromise the data structure and what you actually compromise. So what is the target of our exploit? The target are JavaScript arrays. And this is an example of an allocation of an array. So let's say you allocate an array with 100 slots. Then what you can do is, if you want, you can allocate in the first slot an integer. So you just say array 0 equal 1. Then you can store a double in the same array, an object. So you just allocate a new array inside there. And you can just fuzz whatever data type you want, basically in the array that will store everything you want in there. So you may have doubles, pointer to strings, pointer to function, booleans, whatnot. And clearly, this is not so easy to implement in a safe way. But the more important question that a browser developer would think is actually how would you do it in an efficient way, not just in the secure way. And the answer is numboxing. Now, how many of you actually have heard about numboxing before? Let's see. Well, okay, a few hands. So numboxing is a property of double floating point encoding. So the way the IEEE consortium decided to store floating point numbers was by using the exponential notation. So in this case, let's say you have these two numbers, 1.125 and 11.25. The way they will be stored is you just have the same value for the significand and a different exponent. So the significand is going to be always 1125, while the exponent is going to change between 2 to the power of -2 and -3. Now, the way you see it in binary instead is you will have a sign bit here, which decides if it's a positive or negative number, then 11 bits for the exponent, and eventually 52 bits for the mantissa, which is the significand of the number. So now, as you can see, you have 1.125 here, and the exponent bits are almost all set to 1. What happens when you actually change also the last one and you set it to 1? What happens is that the value changes in none, and none stands for not a number. So basically, you have inside a number encoding, because floating points are numbers, you have a value which is called not a number. And this value, clearly, you cannot use it for any mathematical computations, because it's not useful for that. So what you get, basically, is you have 2 to the power of 53 minus 1 unused values. And this is because you have 50 bits of mantissa plus 1 of the sign, and 1 of the bits of the mantissa needs to be set to 1, otherwise the value would be considered as infinity. And clearly, smart people, smart browser developers thought, well, what if we store pointers in there? Because that's actually a good way to do it. It's actually a very clever trick. So what they do in Firefox 32 bits, and 32 bits in this case is because we're targeting a Nexus 5, but the same technique actually is used on most of normal browsers nowadays. So the only one that doesn't use it, I think it's Chrome, Safari, and Firefox 64 bits. They all use numboxing no matter what. But what happens on 32 bits Firefox is that if you have two values such as these ones, what they will do is out of the 64 bits, they will split the value in two, and they will have the first 32 bits, the higher 32 bits used as tag, and the lower 32 bits used as payload. Now, if the tag is less than a specific threshold value, the whole 64 bits will be used as a double value, so that will be all considered as a number. Otherwise, if the tag is higher than that value, this is going to be considered as a pointer to an object. And then what you can do is, by using the tag, by changing the tag, you can change the type of object. So you may have a string that has a specific tag, then you have a function that has a different tag, Boolean as well, and so on. So what happens here is that if, for instance, you have these values that are stored in the cells of array 1 and array 2 in memory, the way your JavaScript engines will see them is as two different values. So one is going to be a double, and the second one is going to be a pointer. And here, as you can see, you just have the same payload, because the payload is completely identical, but you just have one bit of difference in the tag. And one is a number, and the other one is a pointer. Now, when you think in terms of row-hammer, one bit difference is one bit flip away, basically. So what we can do, and this is our actual primitive on the browser, is type flipping. So what you can do is basically, by triggering a 1 to 0 bit flip on a pointer, you can convert it into a double number, which means you can leak any pointer you want in the browser. And the other way around, with a 0 to 1 bit flip, you can convert any pointer, any double into a pointer. So you can create references to any object you want. So this gives us two primitives, an arbitrary leak with a 1 to 0 bit flip, and an arbitrary craft with a 0 to 1 bit flip. Now, if earlier we were paying attention to the DRAM explanation, you may be wondering how is it possible to get a 0 to 1 bit flip, since row-hammer is actually a leak of charge from memory. And the answer is that the actual logical data that you see, that your CPU sees, is not the data that is stored in DRAM. So DRAM may have like some specific encoding happening at capacitor levels for improving the the storage of the data. And as a consequence, some ones can be stored as zeros and vice versa. So now what do we do? Well, the goal of our exploit was actually to just gain an arbitrary read-write to show that it was possible to compromise the browser by doing so. And the arbitrary read-write is just basically a data structure in the browser that allows you to scan the whole virtual memory. And when you think about arbitrary read-write in JavaScript, the main data structure you think about are array buffers. So an array buffer is basically a byte array that has a header that points to basically this byte array and has a specific size, clearly, since these are all constraint objects. So you'll have these specific boundaries of the array, which means that if you want to perform an out-of-bound access, you will get an error. And as a consequence, what you actually want to do is you want to create a fake array buffer inside the array buffer. So you can use the array buffer as a tool to create your own fake array buffer. And then eventually you also want to reference this fake array buffer because you want to use it as a real one, right? Now the challenges here are two. And the first one is that inside the header there are some unknown fields. So for instance, the garbage collector root is in there, but you don't know this data. And as a consequence, when you want to create your fake version of the array buffer, this is not going to be easy because you need to first leak this data. And the second one instead is that you don't know the data location. So the header, you can leak the pointer to the header by using the bit flipping technique, so the type flipping technique. But this doesn't work for the byte array, right? Because it might be displaced somewhere else in virtual memory. So to solve the second one, which was the trivial version, we can use inline array buffers. So Firefox, what it does is if the array are smaller of a specific size, it will store the data and the header sequentially in memory. So they're contiguous in memory. So once you leak the pointer to the header, you will know the offset to the actual data you just created, and you can leak it this way. For the second one instead, which is a bit more complicated, we first need to get an arbitrary read. And the arbitrary read, we can get it by using the JavaScript string class. And these are Unicode 16 strings. So basically, they provide you a tool that allows you to read any data in memory. And these strings are defined like this in JavaScript. So they have a flag, more or less like this. They will have a flag, then which is the type of string you want to create. Then it will have a length field, which we're going to set to the buffer header. And eventually also a string pointer, which is basically the pointer to the buffer itself. So since we know all these three fields that the header contains, what we can do now is basically we can basically put the string inside the array buffer, so the fake string header, reference it because we already know the pointer to the header of the array buffer, and then leak the data of the header, so you can create it. We can create the fake array buffer. So to recap, the way this works is you just fill the array with some marker values. Then you just trigger the bit flips to see where the location that you found that were vulnerable are. So we'll trigger the bit flip, and at one point you will see a value that changes. And once you find the values to changes, you just allocate an array buffer from the JavaScript engine, and you will reference it twice, because then you will want to leak one of the two references by just triggering one bit flip, right? So the exploit runs in 3 stages now. As we said, you first break ASLR, so you trigger the bit flip there, you leak the pointer. Now you have this pointer, so it means that you can get the arbitrary read, because you just need this pointer for the arbitrary read. So we create the fake string that points to the header of the array buffer, and you will place the fake double value, which looks like a pointer, but it's not yet a pointer. It's a wannabe pointer, basically. And then you trigger the bit flip there that will generate the string that allows you to read the content of the array buffer header. And then eventually, once you leak the header, you can get the arbitrary right just by creating the fake array buffer header, and then reference it the same way as we did before. So this requires 2 bit flips, as we said. We need a 1 to 0 bit flip and a 0 to 1 bit flip. So how is it possible that this actually runs faster than the previous exploit? Well, the answer is behind the fact that we use the GPU for this. So all the previous exploits needed to evict the caches of the CPU, which were too large apparently, and they're quite difficult to evict. Whereas for the CPU, at least the one we studied, it was much faster, and this allowed us to get bit flips much faster than in different exploits. So it runs on around 116 seconds on average. We tested it 20 times, and out of these 20 times, we got the exploit working almost always. And the time it didn't work, it was just because you were not able to reuse the memory they were trying to trigger a bit flip on. So it's not that the exploit didn't work, it's just we didn't have the backup plan of starting again the exploit in that case. Now I'm gonna have a quick demo. So, should be here? No. Yeah. So here, what we have is basically on the left side, I have my own terminal. I'm not showing the phone because since I'm using the GPU to trigger the bit flips, I cannot use it to record the screen. Otherwise, they will clash. So on the left side, I have a terminal that connects to the phone, like ADB. And on the right side, I just have the console to the Firefox browser. So on the left side, I will have the ground truth, basically, and on the right side is the actual exploit. So the moment I start, what we'll do is just allocate a lot of textures. And on the other side, I just want to lick the pointer to one of the main Firefox library, which is the XSUL library. And on the other side, I'm just allocating a lot of memory that I want to scan eventually. So on the left side now, I got basically the base address of this library. On the right side, I had enough allocation, and now I'm looking with the side channel if it's contiguous or not. Now I found a contiguous block. So let me see if I can zoom in a bit on this side. Whoa, maybe this was not a great idea. Anyway, on this side, I'm looking for bit flips now. And I found an exploitable bit flips for a 1 to 0 bit flip, but I'm still looking for the 0 to 1 now. And there it is. So now, as you can see, basically, I found the 2 exploitable bit flips in a bit more than 1 minute. So I have both of the bit flips that I need for the attack. So now what I need to do is basically release this texture and then start allocating a lot of JavaScript arrays on top of this memory. So I allocate 400 megabytes of arrays, just spray the memory with this data. And then I fill it with the marker value, as I said, and then I look for the bit flips. So this is actually where the exploit works, like the actual exploitation part. So what I do is, again, like I just fill it with the marker values, then I break ASLR in the first step. After I found both of the bit flips, I just break ASLR in the first step, linking the pointer to the array buffer. Then I create a fake string, and the content of the fake string is the one I show here, so that's the only content that you need, basically. And then once you lick the header of the array buffer, you can create the fake buffer at the same location, and then you have the arbitrary read-write. And now to show that I have the arbitrary read-write, basically I just try to lick the base of the F library. So I just lick the pointer to a native function. I was kind of slow at typing at that time because I just switched to the English keyboard, so. So as you can see, well, actually you cannot see it now, but the base address is the same now. I have the same pointer here and there. So now I have that pointer, and I try to leak the content of that. So as you can see, I have the elf header to the library, and now if I want, I can just compromise some function pointers or what else. So back to the final part of the presentation. So clearly we follow the coordinated disclosure, and we talked a lot with the browser vendors for this, mostly with Chrome actually. We followed the disclosure and we got help from the Dutch and CSC at that time. And with Chrome we discussed a lot about the possible mitigation for this. Now that time was also the time that Spectre came out, so they were mostly scared about side channels. So they mostly released patches against the timers. Now, for instance, with the new per process isolation, so they have a process per origin isolation that will probably re-enable these timers, or maybe they already did. So who knows, maybe in the future we can reuse this kind of attack vectors. I don't think that the browser vendors consider yet ROM as a threat. And I understand why, actually. So it's not that easy to exploit. It's much harder than other exploitation vectors. But as we show in this work, actually, we can run it quite fast compared to previous attacks. So it should be considered as a possibility in case it's an advanced attack vector, so it's not going to be the day-to-day attack vector, but still it can be used as an attack vector for targeted attacks. And in conclusion, well, we show the first ROM attack from JavaScript on mobile platforms, but the main takeaway of this talk is actually that we introduced the GPU as a new attack vector, and this means that we actually need to redefine the threat model, because as we showed, by just simply shifting the threat model from the CPU to the GPU, we can generate more powerful attacks than before. And so maybe next time it's going to be a digital signal processor or a modern interprocessor with FPGA embedded in the CPU. So you have a lot of powerful tools there that nobody considers, and that's actually quite a big threat. So this is the end of my talk. And now I'm happy to take any question. Otherwise, you can just look up the page of this project. There is a nice write-up of the exploit. And there is also the paper that we published about this. Otherwise, you can ping me on Twitter or also the VUSEC, which is the group where I work. Now, feel free to ask anything.
Do we have any questions? All right, then. That talk went very smooth without any glitches. So thank you so much, Pietro, for that.
Thanks.